Hello, everyone, and welcome to Klara's webinar, ZFS Observability, Extracting ZFS Metrics for Intelligent Storage Insights, hosted by myself, Allan Jude, and Mateusz Piotrowski.
Hello.
So in today's webinar, we're going to take you through a bunch of the metrics that you can get out of ZFS. So what statistics are available and how those metrics correspond to what happens in ZFS, how you can turn those metrics into insights that you can actually get business value out of, and then help you decide which metrics are worth alerting on and what thresholds they should have, and how to configure your monitoring infrastructure and some of the interesting things you can do with that. And then finally, how to determine if your configuration is correct and making sure that the system is giving you what it should be. So first up, we'll talk about the statistics that are available and where you get them from.
Yeah, so in general, we have in ZFS, you have this layers that you can think of when you are observing what's happening on your system. So you have your applications, right? And they are using ZFS. And within the ZFS, you have datasets, pools, VDEVs, and disks, depending on how deep in the whole stack you want to look at. And then you have different tools that you can use to observe those different layers, like ztop for datasets, zpool iostat for pools. You have zpool get for VDEVs, and different things for observing disks, which are usually outside of the ZFS, right? Those are mostly observed from the operating system level. And we also have those interfaces like procfs on Linux and sysctl on FreeBSD that you can use to get some further statistics about ZFS. I'm not sure if we want to talk about anything else here. Maybe we can mention about the thing that apart from those layers where you actually have almost physical items, you also have abstract things like writes and reads. In case of writes, you can observe transactions happening and get different statistics about them. And usually, when I'm observing transactions, I use sysctl on FreeBSD, and I can get a lot of different statistics about both the transaction groups and the transactions themselves.
Yeah, so there's a lot that can happen here, and the characteristics of a write can actually change as they go through the layers. So incoming from your application, the writes can be arbitrarily big. It could be a single 10 megabyte write call or a bunch of small 4 kilobyte writes or whatever. We get directly from the application, and then at the dataset layer, we're counting them there, and we're seeing exactly how they came in from the application. But as they go into the pool, ZFS is going to aggregate some of those small writes into bigger ones, or split that 10 megabyte write up into the records, depending on your record size, could be 128K, 1 megabyte, whatever. And you're going to have different physical writes that are going to come out of those logical writes from the application. And that happens at the pool level. But then when we go to write it to a VDEV, if it's RAID Z, we're then going to break that one big write up across all the disks in the VDEV and add some parity into it, making it slightly bigger, and having to split that up across all the disks. So a single write from your application is actually going to possibly look different at each of these layers as well. And so just looking at any one layer in the stack won't necessarily tell you exactly what the writes are looking like. They might be coming in really scattered from your application, but then ZFS is aggregating them. Or they might be coming in nice and linear from your application, but because of your pool layout, ZFS is having to split them up across a bunch of different VDEVs, or if you're out of space or it's too fragmented or whatever it could be. And so seeing how ZFS is having to change that write as it goes through the layers can also indicate to you where there might be an issue or a suboptimal configuration.
Yeah, it could also happen that your write is going to trigger reads in ZFS. So it does happen that when your application issues a logical write to disk, ZFS may end up reading some data first to be able to write the data, and you can only learn about it when you well, look at the statistics of the layers below you.
Yeah, some examples of that are you might need to read in the rest of a directory in order to insert the new file you're creating in the directory, or if you're doing a subblock update, the write from the application was less than the record size in ZFS, and you're overwriting in place, ZFS will have to read the original record, merge those changes, those partial changes in, and then write out the whole record again, which can lead to this having to read to be able to do writes.
And of course, there are more than like the tools we mentioned in the previous slide are not the only ones that exist, but these are the most portable ones across Linux and FreeBSD. So if you stick to those, you can usually use them across those two platforms. And then what do we usually measure when we measure ZFS? So in case of disks, we measure IOs per second, the throughput, latency, request size, queue depth, and timing. For file systems, which is an alternative name we use for datasets from time to time, we often focus on IOs per second, throughput, or average IO size. And we can also have something in between the disks and the file systems, which are pools. And in case of pools, we focus on transaction group size, transaction latency, or write amplification.
Yeah, so now to start breaking that diagram down, if we look at the dataset stats, so this is for each file system in ZFS, we can get a bunch of metrics about what the applications are doing to that. That helps you see where load is coming from, but also allows you to compare different data sets and see what their workloads are like.
Yeah, and the first example of that is going to be kstat.
Yeah, so if we look at a specific data set, we can see the stats that we get. As newer versions of ZFS come out, more and more stats are starting to appear here.
Yeah, and this interface is what you can find on FreeBSD. And there is a very similar one on Linux. You just have to access the /proc file system, and you can get the very same data out of it. And you may ask a question, what is this object set 0x203? This is one of the data sets you have, but when you ask for the statistics from sysctl, you get this identifier that is internal to ZFS.
Well, yeah, the reason for that is in both sysctl and /proc, using the dataset name, like pool name /something/something/something, made it really awkward in the stats. Like in /proc, you'd end up having to create all these directories and it would get messy. And even in sysctl, / is not normally a character you have in a MIB. And so in both cases, they fell back to it's the internal ID of the dataset written in hex. And you can get the ID of a dataset, which just ZFS get obset ID in the dataset name, and it'll return the number for you to be able to match these up. But as you can see here, if you look at the stats, they actually do have the name as one of the stats to simplify that process. And so just to briefly explain what's here, we show the number of files that have been unlinked and the number of times we've done an unlink operation, which in this case happens to line up, but it could be different. Here we have the number of bytes that have been read and the number of separate read IOPS. And by dividing one by the other, you can get the average size of each of those IOPS. And then again, the number of bytes that have been written and the number of separate write operations that was done over.
Yep. And then there's another example of a tool that you can use to look at your data sets. It's called ztop, and it's much more interactive. So in here, you can see how many reads and how big are those reads per second, and the same for writes, and I think deletion, right?
Yes.
Those are the delete operations. Yeah, so this way you can take a look at what's happening with your ZFS system. And this view is much more easy to parse as a human being, less so far as a machine. But it's, yeah, it's good to have different options.
Yeah, like with the previous stats, we saw those were just counts since the data set was mounted. They don't persist across reboots or remounts. But we saw that it took a whole screen just to show the stats for one data set. Whereas with this view, you can quickly see all of the data sets in one screen, or up to the size of your screen. But it also means that basically it dumps all the stats, then waits a second or whatever interval, and then dumps them again and subtracts them. And from that is able to tell you, the number of IOPS per second and the number of kilobytes per second, et cetera. And it makes it really easy to summarize this data. But obviously, if you're feeding it into a metric system, which we'll talk about in a minute, then you want those raw counters so that you can build graphs rather than having to only have metrics that are averaged out too much.
And then if we go down one layer, we get to pools. And then in a very handy way, the ZFS ships a tool to monitor pool status, which is zpool iostat. And the nice thing is that you can either use it in a very interactive way. I mean, not interactive, but you can ask it to print out the new statistics every second, or just ask it for like one shot of statistics. So depending on your use case, you can either look at it for an extended period of time, or just ask for one for the data for this very moment, and then pass it through to your monitoring system. And it includes various handy flags like -h and -p that makes the output more parsable for scripts. Yeah, it's very handy, and it's the basic tool in the toolkit when working with ZFS.
Yep, and we have our first question from Jesse saying, is it possible to see per file system metadata metrics? My recollection is that ztop is pulling data from syscalls. Well, it's actually sysctl. But yeah, it's actually looking at the read or write system call, while zpool iostat sees metadata metrics, but doesn't split them out by file system. And yes, that's true. So the per dataset kstats are the actual reads and writes done by your application, and don't include whatever extra reads and writes might be caused by ZFS. The main point of the per dataset stats is to be able to tell which dataset and maybe which application is causing the load, whereas the pool stats are more about everything that's happening on the pool. More per file system metrics are coming at the recent OpenZFS Developer Summit at the hackathon. I helped a group of other people work on breaking these stats out further. Again, mostly at the syscall level, where you'll actually be able to see the total number of like opens or creates or mkdirs and rmdirs and so on that happen on each file system as well. But if there are other specific metrics you're interested in, we can look at it, although some of the metadata ones don't necessarily apply to the file system in the same way, and it might not be possible to have per file system stats there. But if we look at our example of what zpool iostat looks like.
Yeah, so that's the basic output you get out of zpool iostat. So if you just write zpool iostat, you'll get information about all the pools, and then you can limit it with by specifying the pool name. Then the next argument would be the number of seconds you want the iostat command to refresh the stats. And I think that -y is for skipping the statistics since the boot. So
yes, so by default, zpool iostat will at startup immediately print out a line with the average since boot, which often is not very meaningful to what you're doing. And especially if you're going to be capturing this into monitoring, you're not going to want that extra data in there. And so throwing in the -y will make it skip that and just print the live stats.
And with -v, you can also ask for verbose mode of this command, which would give you the statistics of VDEVs. That's also handy.
Yeah, it'll break down these read and write operations in bandwidth per VDEV, so you can tell, are all my VDEVs working together, or is one of them slower, or other things that can be really interesting to dig into.
And then zpool iostat has different modes that you can enable or like activate with different flags. For example, we have the -r flag, which can be used for displaying statistics about request sizes. And yeah, that's how it looks like.
So in the previous one, we saw, we did 77 megabytes per second, and it was 2,000 IOPS. If you divide one by the other, you can add, oh, our average IOP is about this big. But that might not actually be true, whereas this view, the request size histogram, breaks down how many of those requests were 4K and how many of them were 64K and how many of them are 128K. And we see that, most of our reads were actually for very large chunks, even though some of them were for smaller. And so the average might have worked out to less, but it turns out a lot of them were on the larger size. And so these histograms can tell a different story than what you get from the averages. But just looking at them doesn't necessarily tell you, this doesn't show you anything about bandwidth. It's just how big is each request. And, you'll see hotspots around there of, most of our application is doing this size of request, and that information can help you tune the pool and get the best performance.
Yeah, because it also tells you how well the aggregation is working.
Yeah, for example, that's the other column here is we see that a lot of our writes were getting aggregated to be at least a megabyte, which is going to give the very best performance on both Flash and spinning Rust. Whereas if we have things that are only getting aggregated to 8K, that saves us an IOP, which on an SSD is maybe not a big deal, but on a hard drive, that could be the difference between 1 megabyte a second and more.
And then another mode we have is the -L, which can be used for showing average latency statistics. Yeah, would you like to explain a bit more about it, Allan?
Sure. In general, this is, we're seeing that, on the first line here, we wrote 838 megabytes in that 1 second, or whatever the period was for that you run zpool iostat with. And we see that, most of the time, most of the reads took about 6 milliseconds to do, whereas most of the writes only took 266 microseconds. And then we see how much time was spent waiting for the disk versus waiting in the queue versus waiting in the async queue and so on. But from this, we see that the average write took 266 microseconds, but it doesn't tell us if some of the writes were really slow. And for that, we can go to the histogram. And this time we see that, for those writes, most of them actually, more than 2,000 of the writes actually took more than 524 microseconds. It was just the fact that there were some that only took 65 nanoseconds that dragged that average down. And in this case, we see that there were no writes that took a really long time, but we do see some reads that took as much as 33 milliseconds. So while the average was 6, there were some that took more than 33 milliseconds. And that might, indicate why your application was seeming slow, even though the average looked like it was good.
And then we go one level lower, and we arrive at VDEVs. So for VDEVs, we can also access the metrics they expose, and those are usually errors, operations, or other things. We have an example of a command in the next slide, but yeah. So this one is I think we already had an example of zpool get maybe in the previous slides. So this is like a very standard interface for accessing well, bits about your ZFS system. Right. So this way you can.
Here we see that the top level RAID Z VDEV has written, what is that, 5 terabytes of data across 95 million separate IOPS, and then we break that down for each disk in that VDEV. And if one of them was significantly different than the others, that would indicate there might be something wrong. But it allows you to see, using this information to know, all right, over some period of time, we've seen this system doing this many IOPS and this many writes. Compare that to what the disk actually saw, and also just, is that, if we plot that on a graph, is that as many as that disk can do? Right? If your average hard drive can only do 200 to 250 IOPS and you're averaging 210, it probably means the disk is as busy as it can be, and you need to get more IOPS somehow in order to be able to get any more performance out of the system. But if the disk most of the time is doing an average of 20 IOPS, then you have lots of bandwidth left. But again, by capturing this and turning it into a metric, you can also tell that most of the time the disk is idle, but at midnight every night, some background batching task kicks off and saturates the disk for as much as it can do for 2 hours, and then it goes back to idle. Can we spread those tasks out in order to get more overall performance?
And then we have disks, and then ZFS doesn't really offer us many statistics about the disks because it's one layer too low for ZFS. So we have to get this information from different sources. So for example, over here we see a Prometheus interface where we plot the metrics we got from collectd. And over here specifically, we see the number of completed write operations. So the orange line at the very bottom is probably a disk that wasn't writing much, but the green lines are, there was some disk writing. So that's how you can get it from collectd, and these are the statistics you can get from the collectd plugin for the disks. So it offers, the most information you usually need for the disks, the basic ones, like the throughput and the number of operations. It also offers some handy statistics like the average read time and write time. Yes, it can be a bit confusing because the names are not, they don't really tell you whether it's a write or read operation. It just tells you 0 or 1. But yeah, it's a very handy tool to export your metrics to your monitoring tool.
Then if we move over to kind of the side of that original diagram, we have information about each transaction in ZFS. So when you're doing things in ZFS, whether that's writing a file or renaming it, that is an individual transaction, and that gets logged into ZFS ZIL, and then groups of those get written out as a transaction group. So normally, if you're doing regular asynchronous writes, like copying a file or whatever, those are going to accumulate in memory as dirty data until you either reach 20% of the maximum amount of dirty data, or it's been 5 seconds since the last transaction group, in which case ZFS will now create a new transaction group and write all that data out, so it will persist to disk. However, those transactions can be delayed for one of many reasons, and when that happens, ZFS has a counter where it keeps track of that, and by monitoring that and alerting on it, you can actually find out, why is my pool being slow? So for example, if the transaction you were trying to do couldn't happen because you were already over your quota, or the amount you had used of your quota plus all the pending stuff that you have in flight that isn't done yet adds up to more than your quota, then ZFS will say, all right, you're going to have to wait until we flesh out all the stuff you've already tried, and then we'll see if you have any space left after all that is reconciled. Or we talked about how once you're at 20% of the maximum amount of dirty data that we flush the transaction group, if you get to 100% there, then ZFS will delay and not let you write anymore until it can flush out all of it, what you've already accumulated, which can happen if your disks are much slower than your application. And then the number of times it was done for the write throttle. Because you have to stop entirely when you hit 100%, ZFS will actually slowly start inserting delay as you pass 60% full on that quota, on that dirty data buffer. And so every time it starts adding a bit more delay, that shows up in a counter here. And by monitoring and graphing these, you can see, oh, there was a big spike there because of something that was happening. It can also happen, if your system is low on memory and the ARC is having to shrink, that can also cause your application writes and transactions to be delayed. And again, monitoring why those are delayed will help you understand why the system isn't faster than it is. And then ZFS also allows you to see, by default, the last 100 transaction groups and some stats about them. This is awfully complicated to get into, but in general, we see the transaction group number, when it happened, the amount of data that needed to be written out, the amount of dirty data, how much was actually written out, how much had to be read in order to do that, how long the transaction group was open for. So in this case, each one of these is 5 billion seconds, because this number is in microseconds or nanoseconds, nanoseconds. And so none of these transactions got so big that we flushed them early, right? So if we see consistently the open time is 5 seconds, that's good, because that's how often we're flushing one if we don't hit any of the limits earlier than that. And we see how much time it took to quiesce that and get it all ready to flush out, how much time was spent waiting to write it out, and how much time was spent actually doing the sync. So we can see as we had more data in this transaction group, it took longer to actually flush it out to disk. But if it takes too long, that can cause the next transaction group to be delayed, and it can, stack up and push back, just like traffic in the real world.
So for those statistics to be useful, you have to observe them over some time. And also when you read the sysctl or the proc file, you only get the last 100 transaction groups that happen on your system. So if there is a lot of things happening on your system, you may not see all the transaction groups happening. So you have to, observe it in a very smart way.
Yeah, basically, if you don't monitor it frequently enough, you'll miss some. If you monitor it too frequently, you have to make sure to align the ones you've already counted. So maybe keeping track, since this transaction group number is monotonically increasing, you keep track of the last one that you saw and only read things that are newer than it, but also watch it for the state, the ones that are open or in quiescing state, any state that's not C for closed, those aren't final yet. So don't count those numbers yet because they're still in progress.
In general, it's not too bad if you miss a couple of those transactions from your aggregation of metrics.
Yeah, and you'd have to be pushing the system awfully hard to go through 100 transaction groups in too short a period. There's also a tunable you can change to make it keep more at the cost of a bit more memory. So if you want to make sure you don't miss any, you can increase that value. I guess before we move on to the next set of stats, there was a question. So Allan asks, we have a workload that writes to ZFS via NFS. We often write 250 kilobytes at a time, which gets turned into several 64 kilobyte writes at the server hosting ZFS. How do we find where the IOs are getting split? It depends. If you see them coming in at 64K at the application level, or like at the dataset level in ZFS, so those per file system kstats we talked about, if they're coming in at 64K, they're getting split before they get to ZFS. And using something like dtrace or BPF trace might be your best bet there. Although with your specific case, I just happen to know that that's happening in NFS. And it's the NFS client and server tuning that you'll have to fix to do that. Or just tune your ZFS to do 64K record size instead. So moving on to the next set of stats.
Yeah, now, so the for the transactions, we spoke about the write path in ZFS. Now the arc is for reading, for caching the reads. So again, there is the sysctl interface to get arc statistics. It's very useful. It offers many, probably over 20 different statistics about arc. So just to give you an example, one of my favorite ones are the ghost hits statistics. They tell you about the situations where you asked about a specific file in your cache or from your disk, and the file happened to be in the cache just a moment ago, but it was evicted because there was no space for it. So if you see a lot of ghost hits on your system, it probably means that your arc will benefit from having more RAM. So it's a nice thing to monitor.
Yeah, what a ghost hit is if only our cache had been just a little bit bigger, that would have been a hit and we wouldn't have had to go read it off the disk. And so ZFS uses that to tune how much of your arc should be for frequently used versus recently used files. And so it can keep changing the split of your arc between those two sizes. But yes, it basically means if your cache had just been a bit bigger, that would have been a win instead of a loss. And so if you see that number happening a lot, you wonder, can we just install some more RAM or change the tuning to get a bit more space in the arc? And then we would have that much more free performance win.
And then, so those were the statistics you can observe in ZFS and use for development or production. But let's talk about monitoring ZFS. So specifically the metrics. So many of the things we saw are very insightful, but you have to actually do some work to be able to interpret them, right? So you don't want to monitor everything that ZFS has to offer. You have to pick the specific metrics that you want to focus on. So, for example, the useful things you can observe are the remaining free space within your pool, because if your pool runs out of space or it goes over 80%, this may result in very bad performance, for example. There's also pool fragmentation that should be kept under observation at all time, because if it's if the pool is too fragmented, again, it's going to be bad for the performance of your pools. Then obviously there is pool health, whether your VDEVs are healthy. The ghost hits, it's also something nice to observe. And there are also other things in the write path, for example, like how long does it take for a transaction group to sync to the disk? How long does it have to wait?
Yeah,
so
well,
if something is out of
how long it had to wait before it could sync, and then how long it took to sync. For example, if a transaction is stuck in the wait state for more than 500 milliseconds ever, that probably means the transaction before was taking too long, or something to that effect, in which case you might want to actually trigger an alert on that, being like, hey, something is causing the system to not be able to keep up.
So by observing those specific things, you can try to get some interesting insights about how your system operates. And then you can use those insights to, could you just change the slide, please, Allan? Yes, then those are the nice things you can get from insights about your, from your metrics, right? So you can detect misconfigured systems, because if something is out of ordinary in your metrics, then it means that maybe you just misconfigured your system, right? Maybe some configuration file is missing, or your application is misconfigured. So for a different host, for a different set of hardware, it just doesn't play well in this situation.
Right. For example, the live question we had, where it's like our application is writing to NFS in 256K chunks, but it's not making it to ZFS in that size. Being able to tell hey, our average is nowhere near 256K. What's going on here? And especially going back to that request size histogram of, sure, our average isn't that high, but is that because there were a bunch of small ones that brought the average down, or was it because none of them were ever actually making it over a certain size?
Yeah, exactly. This is the case of a misconfigured system, most likely, not a bug or something. Yeah. But you can also detect pathological workloads. So maybe your workload is just not suited for the hardware you're having. Or
for example, it's kind of, again, comes back to misconfigured, but if you're writing to files in less than the record size, then you're causing ZFS to have to do a bunch of reading first and shuffling, and it becomes pathological. And maybe you can solve that with configuration, but maybe it means, you shouldn't be using RAID Z to host VMs.
And then if you observe your systems over like a long period of time, you can also detect performance regressions. So maybe after an upgrade of your application or the whole operating system, everything is slower. And then if you have the historical data of how your system performed and how different bits of ZFS performed, you can try to understand what happened. And at the same time, you can also detect hotspots.
Yeah, in both these cases, in order to tell that something is out of the ordinary, you have to know what ordinary is, and that's where having those historic numbers comes in. And yeah, like performance regression could be, oh, this flash disk is not writing at the same performance it used to, or its latency has jumped up a lot. Is it actually something wrong with the device?
Yeah, and then also you can do like the obvious things like detecting failing hardware. Because sometimes ZFS won't tell you that the disk is dying because it's still running, but you can already see that it's getting slower, for example, or it returns errors all the time. Yeah, and those could be the signs that it's time to replace the disk. Yeah, and it's always good to have historic numbers to compare to for various reasons. So once you have all those insights and metrics and so on, usually you want to set up some alerting rules. And we will give you some examples for free, let's say, cases. So you can set up alerting for hardware. So whenever the ZFS tells you that there are read, write, or checksum errors with your VDEV, you can alert on that and have someone investigate what's happening with this specific disk, because it could be that the disk is starting to fail and it has to be replaced. But also it could be a transitive error, right? So it may go away in some time. Maybe it's just a loose cable or something.
Right, and then extreme latency outliers. Sometimes when a disk is failing, it will start acting really slowly, to the point where maybe it takes 100 or 500 milliseconds for each operation, because it's sitting there retrying before giving up or before succeeding even. And depending on your pool configuration, that can make the entire VDEV slow. So having one disk that's dragging the performance of your entire system down, where maybe the option of just offlining that one disk and going and replacing it could restore the performance of your system very quickly. So having alerting on that can be really useful.
And then as we said before, you can have also performance alerts. And for the TXGS, a very popular alert to set up is for the 500 milliseconds in wait state. So if it happens that that the TXG is exceeding this limit, it may indicate that there is something wrong happening with the performance of the system. Yeah, and also observing dirty data and whether it's hitting the limit or not, it's also a good alert to have. And then, of course, apart from all of that, we can also observe the general pool health. So whenever the pool storage capacity is also not the capacity, but the amount of space that is used by a pool, if it's approaching 80%, which is like the common limit to have for pools to keep the performance on a good level, if it's approaching 80%, it's time to add more storage or rearrange how you use this storage.
Yeah, like that one is in particular, being able to have historic data about your pool's fullness and noticing, hey, we're trending up, and in 3 months we're going to run out of space entirely. And it turns out it's going to take 2 months in order to actually order and receive another chassis full of hard drives to expand this pool. We better order it now. And so you can get a lot of information out of that, because yes, and going over 80% starts to have performance impact, but it also means eventually you're going to run entirely out of space and you need enough buffer time in order to be able to deal with it.
And also, once you exceed this limit, your pool is starting to be fragmented, and it's not very easy to defragment your pool. Right. So in order to achieve all of that, you usually have to have some monitoring infrastructure, right? So that you can, when you have a fleet of servers, you need some infrastructure that is able to collect the data from all those different servers and to tell you about the metrics of your ZFS subsystems. So for exporting metrics from servers, you can use different exporters. So for example, the popular ones are Node Exporter, which gives you a lot of information about the operating system and what is happening there in general, but it also has nice plugins, let's say, for ZFS. We have some ZFS-related patches in Klara in the making to add some more metrics to that. They should be published soon. For disks, however, we tend to use collectd because I think on FreeBSD, Node Exporter does not offer the right metrics we would like to see. And then for everything else, you can use OS-specific exporters like Prometheus sys exporter on FreeBSD that allows you to, turn any sysctl you can have on FreeBSD into a metric that is acceptable by Prometheus, and then you can use it in your monitoring infrastructure. Right, and then for collecting and storing metrics, you can use Prometheus. This is a very nice software to start with. It's also very popular. There are a lot of tutorials about how to use it. For visualization graphs and dashboards and so on, you can use Grafana. And for alerting, you can use Alert Manager. It integrates nicely with this whole Prometheus Grafana stack. It's easy to use.
Yeah, and we have some examples here.
Yeah, so over here we have the ZFS TXGS. So we can see some average of how much time, well, those transaction groups are spending in different states. So over here we see that the open state is the longest one, right? We spend the most time in there, and it's all very stable. So it seems that the system is well, there are no pathological workloads there. It just behaves as it should.
Yep. Yeah, in particular, we don't see a large spike in the amount of time it spends waiting or syncing. So that this pool is in a healthy state.
And then over here, we see the rundown of different of write and read IOPS per data set. So as you can see on the right side, we have those hex numbers again, which represent the data sets. If you play around with it a bit more, you can have the dataset names in there if it's necessary. But for a simple use case, you can just have those hex numbers, and then if you see something happening to one particular dataset, you can well, check what this hex represents on your system.
Yeah, it can be especially interesting in a kind of multi-tenant situation where, you know, all right, this one person is the cause of, you know, most of the workload on the system. And if it's not who you expect it to be, that can help you track that down.
And then here we see the ZFS cache hits and misses. So, well, this will tell you whether your ZFS caches are working or not, and if they require some additional tuning.
And we can see that we had a large spike in hits suddenly on this one, and we know that, you know, at that time something interesting must have been happening on the system. So lastly, is how do I tell if my configuration is correct or not? So a lot of these metrics that we talked about today will expose misconfigurations or failures. We can see, you know, we spent too much time having to wait for a transaction group, or we saw that the average size wasn't lining up to the record size and something is off there. And so having these metrics can really help you tell when there's something that's not configured as well as it could be. And it also allows you to compare anticipated performance to realized performance, right? If you know that your hard drives can do at least 200 IOPS, and yet your system seems slow and the hard drives aren't near that threshold, then you know that something might be wrong somewhere that's keeping ZFS from being able to pull all the IOPS off your disk that they should. And you can also find out, you know, when we planned this system, we figured that this workload was going to need this many IOPS, but we see now that it's using twice that, and maybe we need to reconsider how we built this system. And it helps you better understand, you know, what you need out of your hardware, your operating system, ZFS, and the application in order to get the most possible performance. You really want to understand all the layers, and it can be a lot. So if you'd like professional to come take a look at it, then you can reach out to Klara via our website, and we have ZFS performance audits as a prepackaged thing that we can come and do for you and help you figure out where things aren't matching up with what your expectations are and get those fixed to get more performance out of your pool, and just so that you have a better understanding of what's happening on your system. And we can help you build out a nice monitoring system as well. Any more questions? The last question we had was from Matt asking about, do we recommend specific tools? And then the next slide was our recommendations of specific tools. Are there any other questions? And remember, you can reach out to us via our website if you want to request specific services or if you want to get in touch with us. And also go ahead and follow us on Twitter, where we announce all of our webinars. Same for LinkedIn. And then,
Allan, there is
Frederick
one
asked
question.
yes, to go back to the slide with the specific tools. There we are. So that was node exporter, collectd, and then on FreeBSD, there's a tool built into FreeBSD called Prometheus sysctl exporter. It exports all the specific sysctls that are from FreeBSD for consumption by Prometheus. And then Prometheus for the database to store all of this metrics, and Grafana to visualize it, and Alert Manager to make alerts based on thresholds. And we'll have articles on our websites about this stuff in the future as well, to help walk you through setting it up. I think we have time for one more question. So Rich Durso mentions that Node Explorer hasn't worked well for ZFS. That's part of the patches we have, although we're getting most of the stats, like the per dataset kstats, are coming from the Prometheus sysctl exporter in the examples we showed here.
Yeah, one of the reasons why Node Exporter is having trouble with ZFS sometimes is because there are no good libraries, I think, to access some of the statistics of ZFS. And that makes the data collection a bit harder than it could be.
Yeah, there's also another metrics tool available for ZFS. So there's a InfluxDB ZFS exporter that's in the upstream ZFS repo as well. So if you want to get stats out in a different way, you can do that. But we found that this worked very well for us. And yes, a recording of this webinar will be available probably next week on our website and on YouTube. Okay. Thanks, everyone. And we'll see you next time.
Thank you. Bye.